Thank you. Let me introduce myself. My name is Tanasić, and I come from the Academy of Applied Technical Studies, Belgrade, Serbia. I'm a professor of vocational studies, and together with my colleagues from the Faculty of Mechanical Engineering, Professor Ivan Aranđelović and PhD student Miroslav Gojić, are authors of this paper. Nowadays, we need more accessible, efficient, and sustainable fuels in order to reduce the environmental footprint or impact of energy production. One of such promising fuels is green hydrogen, so-called green because it is produced by using renewable energy sources. However, when it comes to the storage and the transportation of hydrogen, the most challenging part is to address the explosion risk and safety associated with the hydrogen application. The primary hazard associated with any form of hydrogen is producing a flammable or a detonable mixture, which can lead to the fire, detonation, and explosion. In this paper, we investigated the influence of ventilation system effectiveness by taking into account several different ventilation strategies in order to increase effectiveness and availability of ventilation with the aim to obtain the high dilution for non-hazardous zone or to reduce the zone 2 area when it comes to the storage or pipelines that are used for the hydrogen transport. Zone 2 is defined as an area in which an explosive gas atmosphere is not likely to occur in a normal operation, but in case of some accident, industrial accident, it can occur, and of course we expect that immediately the plant will shut down. So this situation can exist only for a short period of time. Grade of hydrogen release and classification of the zones is done in accordance with the international IEC standards, which are also taken as a reference in our country. So we start with the velocity of the released gas. In this case, we have to calculate the critical pressure that is based upon of the gas characteristic. Critical pressures are generally low compared to the pressure in the storage tank or pipeline. In the majority of applications, such as like gas supply lines to the fired equipment, like heaters, furnaces, reactors, steam boilers, and other devices. But in case of hydrogen, some storage and transportation will require pressures from 50 to even 100 bar. So in this case, we can expect the choked gas velocity or the sonic velocities when the hydrogen is leaking from this kind of equipment. Now we can see the mass flow can be calculated by this equation, which takes into account some different parameters and also the properties of the gas. So the grade of release is estimated as a secondary leakage due to seal rupture. So that is some case when we have an industrial accident, for example. So we taking into account different leakage cross sections from 0.025 square millimeters up to 1 square millimeter. That's depending on the industrial pipeline connections and also maybe some couplings with the pumps or compressors. So also we take two pressures as a reference, 50 and 100 bar. Discharge coefficient were also calculated in two characteristic values, and also the factor, K factor, which basically shows the influence of the low flammable limit. So if we are unsure about the background concentration of hydrogen in the room, we can take this as a margin of safety by this coefficient. So when it comes to the ventilation, ventilation is very important when we talk about hydrogen storage. Its purpose is to increase the rate of dilution so that we can stay out of this lower flammable limit, and also to avoid the persistence of an explosive atmosphere. If we have a presence of zone 2, that implies a greater risk of the explosion, and in that case, we have to install equipment that complies with the ATEX certificates. The effectiveness of the ventilation in controlling dispersion will depend upon the degree of dilution, the availability of the ventilation. So what kind of ventilation system do we have in that application, and also on the design of the ventilation system. So here we can see the three typical configurations when we have only supply fan for the fresh supply air. The second is when we have both supply and extraction fans, and the last one, which is a local extraction by the hood, ventilation hood, and exhaust or extraction fan. In case of only supply ventilation fan, we have what can happen is that we have to create a recirculating air movement, and then to increase the background concentration of the hydrogen in this particular case. So this number A scenario is not very good in this application. When we carefully consider other ventilation arrangements and the position of extraction points, we can achieve the medium dilution or even high in this case. So we can see the main results of the calculation. So we have basically considered 6 scenarios with different coefficients with 2 design pressures. I said earlier 50 and 100 bar. And we can see here the release characteristic at the last row. When we see the results on this diagram, we can see that the high dilution can be achieved for first and the second scenario, but not for the third or the last scenario, which is with the cross-section of the rupture of 1 square millimeter. Also, the hazardous distances from the hydrogen leakage source are expressed in meters. So we can see that because we have with the high pressures and gases like hydrogen, we usually have this like jet release with the sonic velocity. So some distances are from 1 to 1.4 in the first 2 scenarios, and for the last we have more than 3 meters with the zone 2 requirements. So this is basically the conclusion of the paper. We said that in case of the pressure of 100 bar and opening diameter of 0.25 square millimeters, we need to provide a good ventilation that should be at least 6 meters per second with the velocity. Which is not hard to achieve by the proper selection of the ventilation system. Only in the last case scenario, we are not able to prevent forming of zone 2 and applying equipment with ATEX certificates. So thank you for your attention.